Good morning, guys. Today we're going to start looking at how to solve trigonometric equations. This is actually a two-part lecture, so after this one finishes, make sure you go check out part 2. Now, when we talk about solving trigonometric equations, we've looked at the graphs of trigonometric equations, y equals sine of x. But let's say we change that up, and so it's sine of x equals 1/2, something like that. Well, all we've done, you can see, is replaced the y, any y, with a 1/2. So graphically, what we're doing is seeing where our sine function intersects this line y equals 1/2. Well, as we can see, it happens many, many times because the sine function continues on forever to the left, forever to the right. So we get technically infinitely many solutions to this function. Well, we have a way to generalize those solutions, and it's based on the fact that there's a pattern to these solutions. And we can see both of them occurred at the top of the hill, top of the hill, top of the hill. So we just want to look at where that top of the hill occurs. Now, if we pull it back into the unit circle where we did all our evaluating of sine functions originally, we can see that sine, which is the vertical component of this angle or this intersection point, occurs somewhere in quadrant 1 and then again in quadrant 2. So we get this 1/2, this vertical component of 1/2 in both quadrants. Now what that shows me is that's the top of the hill. Well, what are those angles? Well, we should know that sine is equal to 1/2 when we are opposite 1. So that's 30-degree angle, so roughly pi over 6. That means our reference angle would also have to be 30 degrees or pi over 6. So it's going to be at about 150 degrees. So at 30 degrees and at 150 degrees, we get the two values equal to, where sine is equal to 1/2. Well, what's that? Pi over 6 and 5 pi over 6. Well, that's pi. 1/6 of pi, 5/6 of pi. So we got the two solutions. And then how often does that occur? Well, how often, as I'm going infinitely many times around the unit circle, how often do I hit this pi over 6? Well, how about every 360 degrees or every 2 pi radians? So every time I rotate around 2 pi, 2 pi, 2 pi, I keep coming back to this pi over 3. Pi over 6. I keep coming back to pi over 6. So what we notice is that the angle, whatever it happens to be, plus 2 pi n. N is just the number of rotations I took around to get to that angle. So 2 pi, and n is an integer, okay? It's a number of full rotations. So the angle plus every 2 pi rotations. The other one occurs at 150 degrees or 5 pi over 6. Well, what's the relationship between 30 degrees and 150 degrees? They're supplementary angles. So it's 180 degrees, and that comes back to being our reference angle. Those reference angles are equivalent. So the other solution, because there are two solutions, is 180 degrees or pi minus the angle plus 2 pi n. And we'll start throwing numbers in here and I'll clean it up in a minute. So anytime we're not equal to 1 or -1 for sine, it's going to occur at the angle, whatever we get for that angle, plus 2 pi n, and then the supplement of that angle plus 2 pi n. Now, the reason that 1 and -1 are different is because 1 only occurs one time in that rotation. So it's only going to occur once every 2 pi radians. Same for -1. It's only going to occur once every 2 pi radians. So it's the angle, whatever angle we happen to get, 90 degrees or 270 degrees, pi over 2 or 3 pi over 2, plus 2 pi n. So once I'm at this height of 1, I've got to go a full circle before I get to that height of 1 again. So there's sine, all the solutions of sine. If it's an angle, or if it's equivalent to plus or minus 1, plus or minus 1, it's the angle plus 2 pi n. If it's not equivalent to plus or minus 1, then it's x plus pi n. Or sorry, x plus 2 pi n. 0 is a little bit different, but it's built into these because 0 plus 2 pi n occurs here and here. So we can see it one full rotation. Okay. And when I do the supplement of 0, that's 180 degrees. That's here and here. So I could simplify when it's equal to 0 a little bit more and just say x plus pi n. But if you don't want to have to remember 3 different equations for 3 different scenarios for 3 different equivalencies, you can just remember, if you remember the plus or minus 1, where it's always one solution, rotate all the way around. And then if you'll remember the not equal to plus or minus 1, and that's 2 solutions, the zeros will be built into it. So you'll see that anyways. Now let's look at cosine. When I have my cosines in my unit circle, so there is my unit circle. If I have an angle, I don't care what the angle is, okay, some angle x, well, the other cosine number is the adjacent, the horizontal distance. Cosine is this horizontal distance to get to that point. So there's my cosine. Well, cosine is equivalent, has the same horizontal distance as x when we are at negative x. So these two are equivalent. Cosine of x and cosine of negative x. Just like sine was equivalent for the angle and its supplement, cosine is equivalent for the angle and that negative angle. You could do 2 pi minus x, looking at the angle and then the quadrant 1 version and the quadrant 4 version, or the quadrant 2 and quadrant 3 versions. But I think it's just easier to write the angle and the negative of the angle. Still, it's going to be 2 pi n. Once I have this angle, it's going to take me a full rotation to get back to that angle. If I have this angle, it's going to take me a full rotation to get back to that angle. So cosine, anytime we are not equal to, correct that, anytime we are not equal to plus or minus 1 is equal to the angle plus however many full rotations we need, and the negative of that angle, the opposite of that angle, plus 2 pi times however many rotations. Now, whenever we're talking about cosine being equal to 1 or negative 1, it only occurs once within each cycle. So it's just like sine in that regard. Cosine is equal to plus or minus 1, whichever angle, whether it be 0 or pi, plus 2 pi n. And then lastly, I want to talk about tangent. And we'll secant and cosecant, they're going to be the same thing as sine and cosine. You're just going to change how you get the relationship to get the angle, but once you got the angle, the number of times it occurs is the same. Now, tangent, we know is a little bit different, that it is defined not from 0 to 2 pi, but rather from negative pi over 2 to positive pi over 2. So for tangent, we're going to go really different. Something we very, very, very briefly talked about, where tangent is this intersection point here. And so tangents, that intersection point here, well, that intersection point is going to occur only once, from here, from negative pi over 2 to positive pi over 2. So these heights are the same, but the distances are different. So that means that it only occurs one time. It wouldn't occur again until we get over here into quadrant 3. So quadrant 1 and quadrant 3 would have equivalent distances, equivalent opposite over adjacent, positive over positive, negative over negative. So in quadrant 1 and quadrant 3, they're equivalent. Well, how far apart are these two from each other? 180 degrees, pi. So tangent of x equal to any value, whether it be 1, whether it be 0, whether it be undefined, we know that it has a period. Remember, the period for tangent is pi radians. Sorry, yes, pi units long. So the tangent equal to any value is going to be the angle, whatever we happen to calculate it to be, plus pi n, okay, because we only have to go pi to get one one full cycle of a tangent graph, and then cotangent would work the same way. So these are all the ways we can write the solutions for sine, cosine, tangent, and then again secant, cosecant, and cotangent. But just to recap, sine and cosine, you're going to add 2 pi in to whatever your number of solutions is. Tangent, you're going to add pi into whatever your number of solutions is. Okay, guys, now I want to actually look at what we just talked about and put it into some context, actually solve some simple trigonometric equations. Again, equation equals sign, trigonometric means we have some type of trig expression involved with our variable. Now, if I'm going to solve this, I want to know what it's asking me to do is find out what angle has a cosine equal to -1/2. Now I can go through and reason through that, and I can look at cosine being adjacent over hypotenuse. So adjacent is -1, so that means left, -1, hypotenuse is 2. So I get this triangle. Well, what reference angle is adjacent to -1? That'd be 30 degrees, or sorry, 60 degrees, right? Okay. So if this is 60 degrees, the angle to get to 60 degrees would have had to have been 120 degrees. So x is equal to 120 degrees, or we want to work in radians, which would be 2 pi over 3. So there's my first solution. Well, my second solution is the opposite of that. So if I went negative 120 degrees, I would still get -1 and 2, so I would still get the same triangle. So we would get negative 120 degrees, which is -2 pi over 3. Then we just talked about this is the number of solutions from 0 to 2 pi. The number of all solutions would be where we put the plus 2 pi in on there. So plus 2 pi in and plus 2 pi in. So there are my two solutions to this, all solutions to this equation. Now, if getting the triangle kind of still boggles you a little bit, you still get bogged down on that, I want you to understand these relationships here. So we can use the calculator to solve this also. If I have my cosine of x equals -1/2, how do I move this cosine to the other side? I want to isolate x. I want to know what is the angle instead of what is the ratio. So how do I get cosine to the other side? I do inverse cosine. So I'm just going to inverse cosine both sides. Inverse cosine and cosine cancels. And my calculator tells me that inverse cosine of -1/2 is 120 degrees. Again, convert that into radians by multiplying by pi over 180. So that's 2 pi over 3. And then we would need, the part we have to know is we need the opposite of that since it's cosine. So 2 pi over 3 and -2 pi over 3. So 2 pi over 3 plus 2 pi n and -2 pi over 3 plus 2 pi n. So we can do it analytically by just reasoning through and finding the triangles, or we can do it by using the calculator. I don't care which way y'all used to get it. I want it in radians. So if you're going to use the calculator, you need to make sure your calculator is set on degrees for the mode. Otherwise, it's going to give you like 1.05. And if you know that 1.05-ish is 2 pi over 3, then, more power to you. But most of us aren't aware of that. So what we need to do is make sure the calculator is set on degrees so that it gives us the answer in the nice, neat degree format that we can then convert into radians, because we want to work everything off of radians. All right, let's look at solving tangent of x equals square root of 3. So we go through, again, I'll remind you on how we use the triangle to solve this. Tangent of x equals square root of 3. That means opposite over adjacent. So opposite is square root of 3, up square root of 3. Adjacent is 1. So if we are opposite square root of 3, that means this is 60 degrees again. So pi over 3, same triangle we just had. So there's your angle. Okay, so x equals 60 degrees, which equals pi over 3. And we want to write it for all solutions. All solutions means we bring in the plus pi n. Pi over 3 plus pi n. So there's the solution to that equation. So what that means is every time I take pi over 3 and add some multiple of pi to it, I'm going to get tangent of that angle to equal square root of 3. Okay, let's say we have 5 sine of x plus 3 sine of x plus square root of 3. Normal equation solving. Get all your variables together. So how do I get these sine of x's together? Well, this is a term because it's being added to something else. So I'm just going to subtract 3 sine of x to the other side of the equal sign. 5 sines minus 3 sines leaves us 2 sines equals square root of 3. How do we finish isolating sine? It's 2 times sine, so we're going to divide by 2. So divide by 2, so that sine of x equals square root of 3 over 2. Now, use calculator, use triangles, it doesn't make a difference. I'm going to go with triangles. Sine is opposite over hypotenuse. So opposite square root of 3, hypotenuse is 2. Once again, 60-degree angle because it's 30, 60, 90. So we know that is, what we just say, pi over 3 plus 2 pi n. That's the first one. And then the other one that has opposite square root of 3 and hypotenuse of 2 would be the supplement of that. Okay, so that's going to have to be 120 degrees, is like first example we worked out. So that's 2 pi over 3 plus 2 pi n. So there's the other solution. 120 degrees is 2 pi over 3. 60 degrees is pi over 3. So we can go through use triangle, use calculator, it doesn't matter to me. Calculator is just going to give you the 60, so you'll have to remember to do the 180 degrees minus that to get your second one. But to get that, we just took the pi minus pi over 3. If I can write today. Pi minus pi over 3, and that's where we got the 120 degrees from. And so that's solving when we have this multiple expressions that have trigonometric or have the variables in there. So multiple trigonometric expressions within one equation. That's finding all solutions. You're going to have the plus 2 pi n, the plus pi n, those type of things on the end of your actual answers. Okay, guys, now we're going to look at solving on the interval from 0 to 2 pi. So where before the answers had plus 2 pi n or plus pi n on the end of them, these, we're not going to have that. We're going to have actual angles in there. So it's going to be pi over 3, pi over 6, pi over 12, pi over 12 plus 3 pi, or something along, or 3 pi over 4, something along those lines. So we're going to get actual angles, actual values for x, and we're going to restrict it just to 0 to 2 pi. So the graph could look like anything it needs to look like, but wherever 2 pi is, that's where our answer is going to stop. So we're only going to take the number of answers that showed up in that interval from 0 to 2 pi. Once we get past 2 pi, or up to 2 pi, we stop counting answers. Where before we were saying the equations for all possible solutions. So that's what we're going to look for. So we're going to start out by solving like we just did, where we find the general solutions. Then we're actually going to look at what numbers do we plug in for n to get those specific solutions. So let's say we have cosine of x over 3 plus square root of 2 over 2. We want to get rid of the cosine. We've got to move it to the other side before we can even touch that 3, because the cosine is hanging that 3 on. 3 is part of the angle. So move cosine to the other side either by figuring it out using the triangle, or we can inverse sine or inverse cosine. I don't care which one you go with. If you're going to use the triangle, square root of 2 over 2, I remember that's 1 over square root of 2 where we simplified it. So adjacent is 1, opposite is square root of 2, so that's 1, 1 square root of 2, so the angle is pi over 4. So pi over 4 plus 2 pi n. Let's pull that back from it. So my angle is pi over 4. So what are my solutions? X over 3 is equal to pi over 4 plus 2 pi n and negative pi over 4 plus 2 pi n. So that's where we would have stopped before. I had x, or I had my angle, pi over 4 plus 2 pi n, negative pi over 4 plus pi. That's 45 degrees. 45, 45, 90 triangle. Calculator will tell you that if you want to just do inverse cosine of this. Now I got to finish solving here. I want just x. I don't want the 3. So how do I get rid of the 3? We multiply by 3. So times 3 times 3. Finish everything is multiplied. 3 times pi over 4 is 3 pi over 4. 3 times 2 pi n is 6 pi n. Negative pi over 4 times 3 is negative 3 pi over 4. 3 times 2 pi n is 6 pi n. So this would be all solutions. X equals this. Well, I don't want all solutions like we did in the last set of examples. I want just the solutions from 0 to 2 pi. So what I do is I start plugging in numbers for n. So if n equals 0, what was my original angle before I rotated on around? Well, if n is equal to 0, 6 pi times 0 would be 0. So that's just 3 pi over 4. 6 pi times 0 here would be negative 3 pi over 4. Well, does negative 3 pi over 4 fit between 0 and 2 pi? No, it's before 0, so we don't get to count that one. All right, n equals 1. So I've got 3 pi over 4 plus 6 pi. 6 pi times 1 is 6 pi. Well, 6 pi plus anything is bigger than 2 pi. If I work this out decimal-wise, 6 times 3 is about 18. 9 over 4 is about, what, 2.5? So this is about 20. We want all the numbers between 0 and 6.3. And this right here is 20, so we know that can't work. And then try the one here, negative 3 pi over 4 plus 6 pi. Okay, negative 3 pi over 4 plus 6 pi times 1. So you get the, what, 18 again, minus the 2.5. So you're looking at about, that's my brain did, 15.5. So 15.5 is much bigger than 6.28. So that's not going to work. And we would notice anything bigger than that's not going to work because we're just adding bigger numbers. So it would go from 6 pi to 12 pi and 18 pi because we're just multiplying by 1, 2, 3, 4, and so on. So once you've eliminated an entire row, you get everything that fit within the 0 to 2 pi is your solution. So if I was going to graph this cosine of x over 3, see where that crosses square root of 2, the line square root of 2 over 2? At 3 pi over 4, which we said was about 2.5, is the only time between 0 and 2 pi, between 0 and 6.28, that we would actually intersect those two lines. So it's really taking the problems we did in the last section and just plugging in 0 for n, see what it gives me. Is it between 0 and 2 pi? 1 for n, 2 for n, 3 for n, and keep going until no more numbers are fitting between 0 and 2 pi. Number 2 here has got quite a few more solutions to it. So let's work it. So tangent of 3x equals 1. To get rid of the tangent, we have to answer the question. So what angle has opposite 1 over adjacent 1? So we know that's 45, 45, 90. And so again, we're working with pi over 4. So 3x equals pi over 4 plus pi n, right? Because tangent is just plus pi n. Get rid of the 3, so I divide everything by 3. So x equals pi over 12, 4 and 3 is 12, plus pi over 3n. This would be all solutions. Now we want to limit it to just the solutions from 0 to 2 pi. Excuse me. So plug in 0. Back that up a little. Plug in 0, what do I get? Plug in 1, what do I get? Let's actually pull it over here. We've got some room. So x equals pi over 12 plus pi over 3n. N equals 0. I get pi over 12 plus 0 times that is 0. So what does pi over 12 equal? Pi over 12 is approximately 0.26. So that fits, right? So we get to count that solution. N equals 1. So pi over 12 plus pi over 3, 1 pi over 3, that's approximately, what's that, 1.31-ish? Yeah, 1.31. Okay, so that one fits. Remember, we're looking for numbers between 0 and 6.28. Okay, 0 and 2 pi. N equals 2, so that'd be pi over 12 plus 2 pi over 3. 2 times pi over 3 is 2 pi over 3. We're just adding pi over 3, which is about 1.5. So if I keep adding 1.5, it's 1.05. That's 2.36 roughly. So that one fits. N equals 3. Pi over 12 plus 3 pi over 3, that's pi. So we're going to be sitting at 3.41. That one fits. N equals 4. Now I'll just write down a couple of them because we know we're going there. Pi over 12 plus 4 pi over 3. So that's 4.46. I'm just punching that in the calculator and evaluating. Pi over 12 plus 5 pi over 3. 5 pi over 12, or sorry, pi over 12 plus 5 pi over 3, which is going to be about 5.51. So that one is good. And then N equals 6, which is going to be pi over 12 plus, there's some brain damage, 6 pi. Yeah, 6 pi over 3, which is 2 pi. Which obviously will be bigger than 2 pi if we're adding on to 2 pi, but just if you keep going through it, 6.56. That number is bigger than 6.28, so that angle's too big. So these end up as all of our solutions. Realistically, I should check N equals -1, in which case we have pi over 12 minus pi over 3. But 0.26 minus 1.05 is going to be about -0.81, if I did my arithmetic correctly. Again, not between 0 and 2 pi, so that one doesn't work. So realistically, I should check from -1 on up. If -1 worked, I would check -2, -3. So I'm checking any integers. Just once you find one that works, check the one before it, check the one after it, and as long as they keep working, keep trying them out. Stop once it stops working because you're just adding numbers on. So if it didn't fit, it's not going to fit by adding more numbers on. Same thing here. Work your way backwards. Once you get to a number that doesn't fit from negative integers, just stop, because obviously subtracting numbers is not going to make it fit anymore. So this equation, tangent of 3x equals 1, actually had 1, 2, 3, 4, 5, 6 solutions from 0 to 2 pi. So if we were to look at it graphically, what's that mean? That means we're getting something like three of them. There's one brain dead. Okay, so you're getting like so when we hit 1, it's going to be 1, 2, 3, 4, 5, 6 times before we get from 0 to 6.28. So that's what's happening. This graph shows up 6 times, or we hit 6 intersection points before we get to 6.28. And it's the intersection points are each of these angles. These are just the decimal approximations, because when we get these weird fractions, it's real hard to see between 0 and 2 pi. And I don't want y'all to worry about simplifying and adding all that mess together. I want y'all to understand, the concept of what it is we're finding. Don't get bogged down in the arithmetic of combining all those fractions together. You should be able to combine them, but that's not what we're worried about right here. So you can use decimal approximations to check it, and just leave your answers in terms of those radians. Now, these are the different ways we can solve, or the different types of equations that we can get where we're solving either all solutions, plus 2 pi n, plus pi n, and so on, or whether we're finding this specific solutions from 0 to 2 pi. And realistically, they could put any interval there. I could put 7 to 10 and have the solutions on there. It just depends on the context of your problem. But traditionally, it's 0 to 2 pi because that's typically one normal spread, one full rotation around our unit circle. So in the next, in part 2, solving trigonometric equations part 2, we're going to look at more complex types of equations. The process is the same as far as analyzing the angles, and it's either generalizing it, plus 2 pi n or plus pi n, or we're given us specific angles where we plug in numbers for n. That process is the same. It's how do we get it into this, figuring out what the angle actually equals in that generalized form. That takes a little bit of work. We're going to use factoring to do it. We're going to use our identities to do it. So that's what the next video, the next lecture is on. I need you to check that out. But we'll see you in class tomorrow.